Okay, guys, you are currently taking a test. We got this going, and hopefully within either today or by the end of this weekend, you will have seen this video. So let me flip this. Gets a little squirrely sometimes when I flip my computer around, but since I can't see you guys, I'm just gonna. Okay, that looks like we still are recording. I'm going to turn off my camera because what worth is seeing the top of my bald head? That's the question. Okay, so last time we left off, we were talking, well, we spoke about linear phased arrays, linear sequenced arrays, vector arrays, and then we talked about different resolutions in the past. Of course, we've spoken about lateral resolution. And if you have an object here, excuse me, an object here, that's poor lateral resolution because the one beam is hitting the two objects. Now it can't differentiate. However, if on the other hand, those two objects were further down and one was there and one was there, now one beam is seeing one object, the next beam would be seeing the next object. And I'm also, there's also a resolution of objects in a line. And I'm just going to go ahead and draw a bunch of these because the axial resolution is the same resolution from the very top of the screen all the way down to your far field. Now, I'm showing, I'm kind of showing, I guess, phasing because these outside elements are going first. That created a wave front that was a little bit bowed like that. And it gets down to this point and then actually bows in the opposite direction and will continue to spread out forever after that. I'm also showing sequencing. Since not all of the elements are being fired, it's 1, 2, 3, 4, 5, 6 elements are being fired. And this looks like perhaps the last beam, and we would go back to the beginning and start over. Realistically, there'd be a lot more elements than this. So the last thing we started talking about, if we were to take this and look at it in a side view, we have the elevational resolution, also called slice thickness. So those are three spatial resolutions we've spoken about so far. Slice thickness resolution is the depth, and we don't think about that resolution very often. We think of our beam as being super thin, and it's not. It's actually kind of fat. In fact, it's one of the worst resolutions. I could have drawn this picture here, or that dimension there, even thicker to show that it's not a very good resolution. So we can add on a single row of elements. We probably have some kind of lens that lenses or bends the shape of the beam in the elevational. So that it would be like it would be a permanent lens in this case. So that would be a fixed elevational focus. So fixed in that dimension if it's a single row of elements. Now, and we also mentioned that a disc-shaped, I'm going to move this. Where can you, there you go up there. A disc-shaped transducer, let's just build one really quick here. And let's just quickly add some dimensionality to this. Okay, that's going to create a ultrasound beam that is round in cross section. So in the case of a disc shape or an annular, either way, they're both round, right? The beam shape will be round, and width and elevation will essentially be the same. You wouldn't really even be able to say one is one and one is the other, because they will be identical, because it'll be a circular beam. Our beams we're using, guys, are not circular. They're more, if you saw the bottom of the beam, it'd be more or less rectangular. Okay, so you know, engineers aren't going to end there. You know, they're going to start doing something cooler than that. Just putting a fixed lens in. But that doesn't help us all that much. Why would you want a fixed? You want to be able to change your focus, just like we change the focus in the width all the time. The focus in the elevation can be changed as well if we have multiple rows of elements. Because just as, now what I've drawn here is an attempt. I actually basically took a row of elements and copied it several times and made several rows of elements. Perhaps there's too much going on in here to see this clearly, but let's see. Nice bright green would be good. And let me use a pen that might, let's see. 1, 1, 2, 2, 3, 3. All right. So we phased outside in to create a bowed wave, a bowed wave front, which will come down to a point, a focus. But now we can also 1, 1, 2, 2, 3. See that in this direction now, I've started outside in. So at the same time that in the width, we're going outside in. I should probably redo this so that this is outside in at the same exact time. So now when we create our elevational, now that's just going to bother me. I should have used. Okay. So now what we've done is created a focus in this direction as well. We're already focused here. The beam width is, you know, supposedly about 1/2 of the original aperture. And the same thing here. It's widening out down here. It was wider here. Better to draw that in the same. So that you see that there's a dimension there, right? Okay. So when we focus using multiple rows of elements, and it's not a 3D transducer, this is called a 1.5D. Now, I've never picked up a transducer and said, oh, that's the 1.5D. But let's see, newer transducers called 1 1/2 dimensional arrays create thinner beams with improved slice thickness. Unlike traditional linear phase and convex probes, which have a single crystal occupying space, the 1.5D crystals, array has multiple crystals in the up and down direction. I don't know, back and forth, up and down, across and back. For example, the array might comprise 700 total elements, 100 wide by 7 high. I don't like the term high. It's because it's a depth, right? If you want to say high, you can say high. Phasing similar to that, which improves lateral resolution, can be applied to the 7 vertical crystals. Now they're calling them vertical, thereby thinning the slice and improving the elevation and resolution. But in any case, the width and the height, I guess that's why we call it high, width, height. No, I'd say depth. Well, in any case. Oh, think about this. Elevation and height are synonymous, right? That's why he's using the term height. Okay, fine. I don't like it, but what am I? Either by thinning the slicing. Okay. Actually, I don't like figure 12.37. So 12.36 on page 190 is exaggerated, of course, just for the picture. But what they're not showing there is that they have an acoustic lens. So that's a fixed focus in the elevation of the beam. That is not the width of the beam, that's the elevation of the beam. And then on 12.37, they have a beam that is perfectly straight, square in every dimension. I really don't like that because it does come down to a focus. But I guess it is what it is, or maybe I'm reading the picture wrong. But in any case, 1.5D transducers, they focus in the width and in the elevation electronically. And of course, they steer electronically as well. So they phase in 2 directions, and then they sequence as well. Because you see that I made it sequence by not using the entire row. I only used the last numbers, or the last elements here. 3-dimensional imaging, page 191. They call that a true 2D array. So, 3 dimensionals, but 2D. That's weird, right? Oh, here's a side view. Let's just go ahead and draw that. So, side view, 1, 1, 2, 2. Oh, looks like I needed one more box. That's okay. To truly outside in. So very similar to images that we've already drawn, except now this surface, or that surface, that part of the beam is this part of the beam. Those are the same. So in other words, a side view focused down due to phasing, timing. Okay. Now to 3D transducers, which are actually 2D arrays. Well, that makes sense, actually. The one we just talked about, this 1.5D, they don't call it a full 2D array because it's far longer than it is in depth or height, as he prefers to say. So it is 2-dimensional, but they're holding off using the term 2D array because this one here is truly more of a two-dimensional array. You got that dimension and this dimension. And in fact, I could have changed the arrangement here so that this was more of a square made up of many elements rather than a rectangle. But in fact, the image on page 191 shows a square made up of many smaller elements. Now, we're going to call this a full two-dimensional, 2D array, simply because there's a substantial number of elements in this direction, whereas on the last one, there were multiple elements, but not as substantial. Okay, so beating a dead horse here, right? So the 2D array now incorporates everything. Oh, I'm sorry, got a sad text. Oh yeah, you guys. All right. So I am recording, yes. Let's list what we have here. Actually, let me zoom in so I can write better when it's zoomed in. We're going to incorporate phasing. Phase, do I drop the E? I guess I do. Phasing, which is the same as timing. Let's put that. Timing. Underneath phasing, I'm going to add electronic focus, and more importantly, for three-dimensional, electronic steering. And we also incorporate sequencing. And that is in both dimensions. That's without a T. All right, dimensions. Anyway, both dimensions. Phasing, electronic focus, and especially electronic steering and sequencing in both directions. So this guy incorporates everything. And it does it in more than one direction. So let's think about that. Now, I have spoken about the fact that what we're really imaging is a page. If your body, or for that matter, your baby, is a book. What you see on the screen is a single page of that book. Imagine taking a page, ripping it out of the book, placing it on the screen. That's what we see. We see cross sections of the body, cross sections of your baby's body if you're pregnant. It is one page. Now, let's think about it this way. A three-dimensional image is many pages, perhaps all the pages, depending on how much you're 3Ding. So if I were to take, instead of one page out of the book, I took 300 pages and took a picture of each one of those pages, added all of that information up into a volume. 3D is also called volume imaging. I've added all those together. Now I have a volume of information. I have a three-dimensional picture. So, oh boy. I'm going to pause this for a second because I'm going to have to draw some things and I don't need to have you watch me doing that. So pause. Okay. Magic of Zoom and Sketchbook. I am back. I just spent a few minutes drawing some pictures. So I just kind of want to reiterate, I really like the book analogy of what we're actually seeing, because most of us don't know. I would say, I would hazard the guess that even some sonographers out in the field, they know it, but they don't know it. You know what I mean? It's like, well, here, I can temporarily put my face on the screen here. No, actually, I'm taking off. I'm going back to whatchamacallit, tablet mode. Okay. They know it, but they don't know it. They don't really think about it. They don't really think about the difference between a three-dimensional and a two-dimensional. It's not just simply that you see a face or you don't see a face. There's a pretty big difference there. And so here's my book. Here is my this is my actually my body book. My body book. All right. That's represents the human body. We put our transducer down. Actually, now that I think about it, let's erase that right there. I'll put that over here again. Body book. So that represents the human body. I put my transducer down. In this case, I'm going to put the transducer down in such a way that we are going to be seeing the edge of the transducer. In other words, we're not seeing, normally I build a transducer such that it looks like that, right? Well, that's not what we're looking at. We're looking at the side. So if I were to draw this again, I might just have it like that because it's a profile. We're looking at the profile view of the transducer. And there's a reason I'm saying it that way. All right, because in the profile view of the transducer, just like I drew these profiles, that's a profile view. This is a profile view. So let me actually circle it. Profile view, not the width view. In a sense, the profile view, that's the elevational dimension. In a sense, it doesn't exist. It does exist, but we don't, remember I already mentioned that the elevational dimension we don't usually think about, because the elevational dimension, that entire dimension, is seen on the screen all at once. And so this is our screen. So if I have my transducer down like this, here, I'm gonna draw just a little more dimensionality to this. Gosh, what color was I using? I guess it was around there. Add a little bit of dimensionality. Okay, so there's my transducer side profile view or elevational dimension. Yes, I always put a T in dimension. I know it's wrong. It's just a bad habit. Okay. So, and when I say body book, what I'm really saying is that here's that transducer again. Here's that transducer, and here's the one page of the book. we see one page at a time. Well, we learned that due to slice thickness, we actually see many pages at one time. But we have to assume, we have to imagine that we're seeing one page at a time because that's what's shown. So that page, what does that mean? That page is, and we'll make this a square because that's just simply the easiest, is your image. So in the case of a book, you might see handwriting. I better take that out because there's some kind of writing in this book, or if it's for John, actually, let's make a book for John here. So it has to be up. There we go. It's a picture book. But in any case, well, so there's the baby, right? Actually, no, I don't want to call it the baby. I'll just call it a picture book, and this is for John. And he's playing sports. It's a book about sports because that's so important in life. Anyway. Anywho. So that one page is all we see with the transducer. Now imagine instead that we have a transducer, and this is a 1D, our regular transducer, a one dimension. It's one dimension on the element face. Might be two dimensions on the actual image. So technically 1D makes a 2D. Well, it looks like I just wrote image. 2D image, and actually a 1.5 or 1.5D also makes a 2D image. A three-dimensional picture is made out of a 2D. Now imagine if I had a 2D and I can steer the beam in multiple directions. Critically, let's just say for this picture, I'm just going to steer the beam in a direction like that, and a direction like that, and then sometimes I'm steering down, and sometimes it's off to this side a little bit. I'm able to, without moving my hand, without rocking or anything, I'm just staying still. I am now automatically steering back and forth. Now, it's instead of a page, it's pages. This page is seen, and that page is seen, and that page is seen, and this one, and this one, and this one, and this one. And now, a 2D. That's very confusing, a 2D transducer, right? Well, when they say 2D, they mean the surface of the transducer has two dimensions, height, width, and let's see, 2D, that makes a 3D image. It images all the pages in the book, puts them together. Now, our 3D image, of course, is displayed on a flat two-dimensional screen. So we're not truly getting a 3D image. We are getting what it looks like 3D. It's a trick. It's a trick that three-dimensional cartoonists and three-dimensional ultrasound builders, manufacturers are playing on our eyes. It's still two dimensions, but it gives us the idea. It certainly looks like three dimensions, right? And so now we don't have that one book anymore. We have all the pages. I don't know how to draw all the pages dimension. Now, if you actually think about it, with 3D, they have to render an image. Why is that? Why do they have to render an image? If you got all the volume, you've got all that information, why would you render it? Well, if you stuck your face, what would be a good analogy? Well, the verbal analogy is you can't see the forest for the trees. And that verbal analogy means that you're so close, you're inside of the forest, and you don't see a forest because all the damn trees are in the way. Makes sense. It's kind of it's a funny little saying that I rather enjoy that saying. And it kind of with 3 dimensions, if you were to take all of that information and display it, all of the rendered information, all of the gathered volume information and display it at once on the screen, we would see nothing but a blob. We would just see an infinite shade of gray. We wouldn't be able to see anything. You can't see the forest for the trees. And so what rendering does is basically finds all the relevant information. Let's say we're doing a baby's face as shown on page 191. Remember, ultrasound sees through things. It doesn't see surfaces of things. So how do we get a surface image of a baby's face? That's not how ultrasound works. It doesn't just stop at the face and take a picture of it. This isn't a camera taking a picture with light bouncing off of your face and back to the camera and it takes a picture. No, this is sound that went through that baby and went through its brain and through its eyes and out the back of its head and bounced back off mom and came through. There's a mess of material in there. And so with rendering, the machine is smart enough to take the relevant information and say, okay, I am going to pay attention to the surface echoes, and I'm going to ignore all the echoes that came after that. And so it's able to figure out what a surface is. By the way, if the baby's face is up against the placenta, you cannot get a good ultrasound 3D image because the surface is now the placenta. That face has to be separated. So once there's amniotic fluid in front of the face, the machine is able to say, okay, this is some kind of surface. I'm going to take this information and I'm going to render it. Rendering means really adding skin, adding a photo-like texture onto the surface. And so in the case of a baby, all the colors you see, you will find patients out there who think the color that they see on the image is the color of their baby. And I am not kidding. Fights can break out because the baby's the wrong color. Now that's a particularly, and that doesn't happen every day, but that's how some people think about it. But it's not. Everything on the screen is just an echo. So if you're seeing a baby's face, it is a bunch of information that has been rendered or created basically the same way you render a 3-dimensional modern animated cartoon are done on computers and computer rendering. So let me read this page real quickly. 2D. I'll tell you really quickly. I worked with a Southerner, and he was asking me if I did 2D. I'm sorry, 3D. 3D. You do 3D, and I'm like, I'm sorry, I don't know what that is. He said, you an ultrasound tech, and you don't do 3D. You don't know what 3D is, and I finally, I was like, oh my God, 3D. He was a soldier. All his friends were making fun of him after that. I'm not saying all Southerners. I'm just saying certain areas of the South has some pretty thick accents. He was definitely a hillbilly accent. Anyway, you may encounter the term 4D imaging. 4D, of course, 4D imaging, that's the dimension of time. So the only difference between, you have a 3D image on page 191. If this were a Harry Potter book and it was moving, it would be 4D, it would be the time element. Rendering creates rendering photo-like images, 3D renderings often performed offline on standalone computer system. Yeah, no, not so much anymore. 3D rendering occurs as right there in front of you. Under these conditions, 3D rendering is post-processing, an example of this technique. Lion King's, Toy Story, those are 3D rendering. Okay. Oh boy. Chapter 12 is almost done. We go into a very different subject all of a sudden, but I do want to get this finished. Let me hit pause on my recording so you don't have to sit there watching me do this. Okay, I am back. So special topics, page 192, side lobes and grading lobes. We don't have to necessarily deal with side lobes, we deal with grading lobes, but we still have to learn about both. If you guys remember, actually, I should have kept something over here. Well, this is good enough. I'm sorry, I should have erased more of this as I think about it, but that's okay. We'll just do this and this and that. And let's see, as I draw in kind of a wave front coming out. Okay, so we have our Huygens wavelets, of course, and this Huygens wavelets occur with both single element and multi-element transducers. Here I have a multi-element transducer. Remember, we say that the beam is a narrow beam. It does not spread out. Individual bubbles of sound do actually spread out, and so there is a spread going on like this, except it's so weak that it essentially doesn't exist, because out here it's just spreading out and getting weaker and weaker as it goes, whereas here we have all sorts of areas where let's see, all this constructive interference. Let's just, we have to imagine there's more constructive interference here. And so it creates a sound beam, right? That's what our beam is. There actually is sound traveling outside of the beam, but it's weak. We don't care about it until we do, because as you can see, just from my very, very primitive drawing, we do occasionally get a crossing of two peaks. So we do occasionally get some constructive interference on the outside of the beam. Let's just pretend there's one there. I didn't draw this very accurately. Well, that unwanted, mistaken interference out there creates basically weak, but not that weak beams. So on side lobes, and I'm not real 100% sure why they have different terminologies. I know but they're basically made the same way. They have a different shape to them, I guess, but Because remember, there are wave front Huygens wavelets here, and that's making the beam of sound. But as we just showed over here, there are waves that come out to the side. Now, the book shows, and the book shows that these occur when it comes to side lobes, these occur after the focal point, and then as these waves are, perhaps as they're spreading out more, we still have a beam of sound with all these overlapping waves causing constructive interference, but they start to be found outside of the beam as well. And so at some point, a weak beam is produced, a side lobe beam. So let's think about this. We have to the reason why this is a problem is we're going to have to evaluate. Sorry, I thought one of you jumped on and I heard something for a second. We have to violate an assumption here, or an assumption will be violated. The assumption that we always think of is that the beam is very thin and it travels in a straight line, and every echo we hear is from the beam. And remember, a beam is really just one pulse, right? But that's still, we pretend it's a constant beam, but it's a single pulse. So we assume every echo is coming back from different objects inside of the beam. Right? And of course, with a single element transducer, that thing's probably being spun around, so it's a mechanical transducer. It's spinning, creating different beam lines, but still, every beam, every pulse, we assume all the sound that is coming back came from something that was inside of the beam. Well, now here, look at this. We're creating a stronger than, we're creating it's a weak beam, but it's strong enough to create an echo. Let's use a different color. Let's use red. You see what happened there is that we received an echo from something that wasn't in the right place. It wasn't inside of the beam. So think about what does that do to your picture? It's now the computer has to assume, this is getting messy. Let me zoom in a little bit here. It has to assume that whatever was out here that created, let's make it a red dot or red something. It can't make the assumption, it can't say, oh, that echo came from over there. It could only think that the echo came from here. Real imaginary. So even though single element transducers produce side lobes, I'll tell you, this is what you're dealing with. A lot of what you're dealing with on the screen when you have, why is it so fuzzy? Well, this is a big part of it. a real object outside of the beam, outside of the main beam, if it is hit by a strong enough side lobe, will be heard, or heard or seen, whatever you want to think of it as. But the transducer and the machine can't possibly know that it was outside of the main beam, so it's going to put it inside the beam, which means you're going to see something on your screen that is misplaced. The thing about this is that this doesn't always happen. And this real object here had to be an object that reflected a lot of sound. So a echogenic object or structure. Because if this were a hypoechoic structure and getting hit by a weak side lobe beam, the echo never would have made it back. So it's a combination of side lobe and echogenic object or echogenic structure outside of the beam, outside the main beam, produces an echo, and the machine thinks it's here rather than where it really is. So that's side lobes. There's not much we could do about side lobes. They degrade lateral. Typically, the main beam is much stronger than the side lobes. However, the lobes are sufficient intensity. Structures within them can generate reflections. Reflections degrade lateral resolution. Grading lobes are similar. Grading lobes, according to your book and everything, and everything else, is they're created a little bit higher up. So I'm going to go ahead and put a lobe here, maybe even a secondary lobe there. Grading lobes. Well, let's draw in really quickly what might be causing these. So we have, of course, we have a wave front. Let's do one more here. My wave front's bowed in the wrong direction a little bit. That's okay. That's not what I'm showing right now. I'm not showing focusing right now. Once again, and I didn't draw this perfectly, but you could imagine that out, well, actually, no. Let's add a, shoot, what color was that? Kind of carefully add a few. Okay, now I've contrived to create what I need to create. I created, of course, once again, some constructive interference outside of the main beam. Now, there's all sorts of constructive interference in here, but that's where we want it, and that's what creates a strong beam. So once again, very similar to side lobes. Simply put, the beam is not as narrow as we think it is. There is a width. There are extraneous sound waves going off outside of the beam, and when those line up well, they can create these grading lobes. And once again, an object out here, let's just, I'll put my red object again out here, creating that echo. goes back. What does the transducer see? It cannot possibly know that that's where the echo came from, so it puts it here. Of course, this is a exceedingly wide beam and an exceedingly small object, but you get the idea. This is, so it thinks, dotted line, that's what it thinks happened, because we violate an assumption. The assumption is that all sound comes from the beam, and unfortunately, or all echoes come from exactly where the beam is. And unfortunately, that's not the way it is all the time. So how do we fix this? Well, there's a couple of things that we can do. Obviously, if you think about it, these middle elements aren't causing the grading lobes. These middle elements they're causing all of those interactions. Those are all good interactions, but any grouping of elements has to have outside elements. Just erase a little bit of that. Okay. Every grouping of elements has to have an outside, right? And so what we can do is weaken the pulse, the voltage. That's called apodization. Apodization. That is weakening voltage to the outside PZTs, elements. Since lobes are created, reducing the strength of the side and grading lobes can be achieved through a process called apodization. And if you are a quick learner, on page 193, he says, since lobes, this is the first paragraph, since lobes can create artifacts, it is best to eliminate them. Reducing the strength of side and grading lobes can be achieved through a process called apodization. Well, you can't use apodization on a single element because it's one element. How are you going to reduce the sound? I suppose you could, if you have an annular array, you could, yeah, I suppose the outermost ring can be hit with a lesser voltage than the inner rings. But certainly with multiple elements, you can weaken the voltage to the outside elements, which will weaken the grading lobes themselves. The other thing that can be done is subdicing. So strength of the spikes. Yeah, subdicing of each element in a linear array transducer also reduces grading lobes. This, I don't understand why. I'm just going to have to teach it to you, and you're going to have to believe me. With subdicing, a crystal is divided into a group of smaller crystals called sub-elements. These elements are electrically joined and act as if they are single crystal, which reduces grading lobes. Okay, so every element is subdiced, and this produces less grading lobe. Not 100% sure exactly what that even means, but if we were to subdice this transducer, we might, let's use a different color so we see the subdicing. And of course it's 1, I don't like the 2, I don't like the color. Let's say we chop it into 1, 2, 3, 4. So it is sliced in the 4, but it still acts as 1. All right, these guys are all held together by a wire. Let's do a little, we'll do a little wiring in between each one of these. That's supposed to indicate that they're all electrically connected. So when ultimately, here, I'll put that wire up here too. Ultimately, when the main source of power comes in, hits right here, hits basically all of these sub-diced elements at the same time. And so they all act in concert, but they reduce, and every element would have this appearance. So all the way across. That is called sub-dicing. Oh my God, dynamic aperture. Oh, one more subject. We got to go through it though. Got to get this done. I'm sick of chapter 12. Dynamic aperture. Oh my gosh. Okay. All right, guys. I'm really sorry about this. Let's just jump back to your 3D brain again. I drew these nice pictures down here, and I forgot that I drew a picture up there, or I added to this picture up here. What I was talking about before is that, you know, in 1D or 1.5D, you get a 2D image, and that 2D image is basically thought of as one single page in a book, due to the fact that we don't have that precise of a beam. We could think of it as more like maybe 25 pages of that book, but still it's considered one page, and it produces a one-page information. 3D image. Oh, this is what I should have drawn here is basically what I drew up here. So a 3D image is those multiple pages. 1, 2, 3, 4, 5. It's going to be actually a lot more than 5, but and each one of these is done by sweeping the beam or steering the beam in a slightly different direction. So the beam was steered in this direction to get number 1, steered quietly a little bit less to get number 2, steered 3, steered 4, steered 5. So there. Okay, back to what we were going to talk about. I think I can keep that over there, and we'll just use this side of my array transducer. Technique called dynamic aperture. Oh my God. So we just learned about dynamic focus, receive focus, I should say, not dynamic focus. That's another thing. That's the first thing we learned. But dynamic receive aperture. Okay. Let's do this again. I have an object. Why did you not draw anything? I have an object here. A sound beam was created and an echo was returned. That's spreading out echo. Remember, a beam of sound goes in, but not a beam of echoes comes back. It's a spreading out of echoes. Okay, so let's just draw these echoes in again. This is the wave front. If we could see a wave front of an echo, that's how it's going to come back. A technique called, on page 194, called dynamic aperture can be used to make a sound beam narrow over a greater depth of depths. Transmit hole and or the listening hole. Okay. I actually almost forgot. There's dynamic aperture works in both directions. And I kind of skipped to the echo part, but it actually works in both directions. Let me pause. I literally need just 1 minute to gather my senses here, but let me do this. Okay, only 20 seconds. I just had to remind myself. Remember, we learned that different aperture sizes. So let's take an aperture of this size, 3 elements wide. Aperture size creates different natural focuses. Let's take another aperture, 1, 2, 3, 4, 5, 6 wide. Now we have another aperture that is 6 wide. Once again, didn't draw that like I wanted to. That's the natural focus for the 6 wide aperture. I can go on and on. I can go across this entire face, I suppose. So each pulse, each focal point can have, if we're talking about dynamic aperture on the way out, the actual creation of the sound beam, you could only have a dynamic aperture if you have multiple focal points. Each focal point will not only be phased differently because phasing creates different focal points, but you might as well take advantage of the fact that a natural focus for a deeper structure could benefit from a larger aperture a larger aperture would automatically create a deeper focus. A larger aperture and phasing you could use that in different ways to create all sorts of different focus points. So a dynamic aperture doesn't have to be 10 elements every time, every pulse. It could be 8 elements for pulse 1, 10 elements for pulse 2, for focus 2, focus 1, focus 2, and the focus 3 could have 12 elements being used. Because that makes it's just adding to the pie. It's not absolutely necessary. You could not use dynamic aperture and get the same effect simply by phasing, simply by timing your outside to inside elements. So that's dynamic aperture on the way out. That's the one I almost forgot to tell you guys about. But that's okay, because now, actually, I'm gonna move my little star over. Here's my little star. Now a green star with purple echoes. Actually, let's do a purple star as well. In fact, I'm going to put my purple star here. Okay, purple star, purple echoes, green star, green echoes. That makes the most sense. Now, dynamic receive focus. What did that do? Okay, that as the sound beam is coming back, the echo is coming back. There's a variable amount of spreading out of the echo, but this can be predicted. They know how much an echo is likely to spread as it comes back to the transducer. And it knows that the middle of that spreading out of that arched echo, that echo that's kind of shaped like this, they know that the middle is first and the ends are last to make it back. And so inside the computer system, it says, you know what? No, this wasn't a round object creating this. This was a flat object, or in this case, a star, that created a rounded echo. But the fact that it was a rounded echo, that's just the way sound moves normally when it's bouncing around. And so we phased the receive echoes. Just as we phase the transmitted sound, we're actually able to phase the received echoes. Well, there's another component here. That we could also see going on. And that's the amount of elements that can see an echo from a certain depth. If you're from the purple depth, you'd only expect, let's see. You'd only expect those elements to hear an echo from that depth, because the echo's not, it's spreading out, but it's not spreading out that much. There's a certain amount of spread that you can expect. And for the green element though, I'm sorry, the green echo, now we're filling in so now we're filling in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. So it's a variable aperture, a dynamic aperture. And the same thing on the receive. Yeah. And so the listening elements change with time. Let me add a third color in here, just as a kind of as an understanding. Let's say that the red elements, I'll paint the top. There we go. These elements were stimulated to create the sound wave, or the sound beam for the green. So you had 1, 2, 3, 4, 5 elements create a pulse of sound for a focus of that depth, which happens to have a star in it. When that creates an echo that comes back, and that echo in turn spreads out, and it ends out using 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. But on the other hand, this focus here perhaps only used, let's just say 1, 2, or 3 elements were used to create the focus for there. So that's all well and good. 3 elements were used to create this focus and phasing. They were phased and dynamically apertured. So 3 elements made this beam. It focused down to something, a star that happened to be at the focal point. That star created an echo that came back, but that echo ended up using, oh shit. All right, well, okay, same number, 3, 1, 2, 3 elements. So that's not so dynamic, is it? It's 3 and 3. But then the next time we made a focus, we used 1, 2, 3, 4, 5 elements, created this red beam, which focused down to the star here, which in turn created an echo that spread out. And rather than listening with the same number of elements that the beam was created, that created the beam, manufacturers said, you know what? No, when it comes from, let's just make up a number, 39 microseconds or 3 centimeters away, we might use 5 elements to create that sound beam, but we're going to listen with 10 elements because we know the sound beam spreads out. Combine that with dynamic focus, no, receive focus, dynamic receive focus, and you get an even better picture. Whew, man, that is a hard concept to talk about, but I believe I did it. And my God, you know, that entire concept is covered in 4 short paragraphs. So before I sign off, and this is the last thing we're going to learn, before I sign off, let me just say this, guys. I do spend time thinking about how to explain this, how to create an image, how to make you or help you to fully understand what's going on. When you look at his book, and actually, if you were to go to his seminars, and I'm not complaining, I'm not saying anything bad about him. It's just he's perhaps more realistic than me, or more to the point anyway. He only teaches you what you have to know, and damned if you understand it or not. He basically is saying, I don't care if you understand it, just remember this, and then get the question right. I'm not saying I'm better. I'm not saying that his is better. I think we both have our ways of doing things. I don't have a problem with that. I'm afraid that if you don't, I feel like if you truly understand what's going on, you'll have a better understanding overall of what's going on, and you'll be able to interpret questions a little bit better. But if a concept like this is just keeps going over your head, then ignore everything I said and just read carefully page 194. Read it several times. Did someone just jump on? Or is that me? You want to save change? No. Anyway, do the questions in the chapter, do the questions in the back of the book, and just memorize. In the end, guys, it does not matter. All that matters is that you pass the SPI. And so if me going through this is over your head, or if I'm not explaining in a way that's digestible to you, then fine, go to the book, go to the internet, and use any method. So I don't care. I'm not going to be insulted. All right, I'm going to sign off now. Hopefully, you guys should all be done with your tests by now, and hopefully we'll see a bunch of amazing grades. Adios.